we're going to use the Euler method to approximate the solution to this particular initial value problem. And let's say we're interested for some reason in the value of the solution at 1.5. So that means clearly we're starting our problem at a time value of 1. So we'll, out of illustration simplicity, let's take 5 subintervals, and it'll be on the interval from 1 to 1.5. So that means the length of each one of these subintervals will be 0.1, so a tenth of a second if you want to think of it that way. And these would be the actual grid values we have. So the Euler method says this: if you're interested in calculating the solution, the approximate solution at step I, you should take the solution you got and the step prior, and then take the right-hand side of the differential equation and plug in all of the values from the step prior. Now, in this particular problem, this is the function f of t and y. So what the Euler method requires is the initial starting value. So there's y of 0 is 1. And now we need y1. So this is going to be y0. It's going to be 2. Actually, maybe I'll write it explicitly here. It's going to be f of t0, y0 times h. And in our problem, that's going to be 1 plus 2 t0 times y0. I'll write that out up here. y0 plus 2 t0 y0 times h. So in our problem, that's going to be 2, 1, 1 times 0.1. So that's going to end up giving us a value of 1.2. So the first step, the approximate solution there is a 1.2. y2 is going to be y1 plus f at t1 and y1 times h. So this is going to be 1.2, 2, t1 is the location 1.1, y1 is the value 1.2, and this is 0.1. And so this will end up giving us 1.464. Okay. So you can see, as I mentioned before, we are just constructing a list or a sequence of values. y3 will be y2, f of t2, y2 times h. So this is going to be 1.464, so the value we got in the step prior, 2 times 1.2. The solution value we got prior times 0.1. So y3 is going to end up giving us 1.81536. So I'm hoping that you can see the whole process here. I'm just going to skip the values here and tell you that y4 will be 2.28735 and y5 will be 2.9278. And this is the approximate solution that I'm interested in. So in these 5 steps that I used to calculate the approximate solution, this was my ultimate goal here at the end. Now, we are lucky here because in this differential equation, or in this initial value problem, we can find an exact solution. We deliberately chose a problem that has an exact solution. It's a separable dE, and that means that the solution here is going to be e to the power of t squared minus 1. And so what this allows me to do, and hopefully gives you some indication of why we bother trying to find explicit formulas, is because we need test cases. And here, this is the exact solution. So in this picture here, this curve represents the exact solution, and this piecewise linear approximation is our numerical approximation due to Euler's method. And here are our grid points. There's T0, T1, T2, T3, T4, and T5. So you can see that at each one of those locations, I've got a dot, a circle, representing the height predicted by Euler's method. there's an error. As we mentioned, at every step, there's an error. Now, depending on how the exact solution behaves, that error may grow, that error may shrink. But what we really want to know is how accurate is this solution. So the exact solution at 1.5 is about 3.4904, and the approximate solution at this value, we're going to call it y5, was about 2.9278. So this is about a 16% error. We're off. This isn't really good. This kind of error is unacceptable. It's too large for real scientific applications. So if we are going to hope to keep using Euler's method, or perhaps any other method, what we really need to understand is the sources of these error. So where can error come from? On a computer, computers only have a finite amount of memory to store for each digit. So there's what's called finite precision, or what ends up happening is what you get in the case here called rounding errors. As a very simple example, 1/3 has an infinite decimal approximation of 0.33333 forever. But if you're going to store that number on a computer, at some point you have to cut it off and you have to make a rounding error. And that introduces problems. Now, rounding errors are more challenging to analyze, and we don't typically get into them. We're interested in something called truncation error. Now, truncation error is easier to understand, and it's much more closely related to the steps we took to come up with our approximation. So remember that when we derived this with the Taylor series, we decided to expand the function near the point we were interested in, and we had several terms. Now, in Taylor's theorem, we are interested in the first point, let's say, and there are infinitely many derivatives that come about with all of these terms. And there's only an equality when we include all of those infinitely many derivatives. We decided to cut or truncate this. Now, when we make this decision to cut or truncate, we are left with a certain portion. So it turns out that we make an error. We make what's called a truncation error in doing this, and it's called a local truncation error. And it turns out that the accuracy of our method is proportional to what power of h is left. So the accuracy is related to the power of h that remains here. So the Euler method is, we say, big OH, so it's a first order method. And what it tells us is that if we decrease the h size, if we make the size of the step smaller, that means that the error will also decrease by the same amount. So if we double the number of points, what we'll end up getting is half the error. Right? So if the size becomes smaller, the error becomes smaller as well. That's a general feature of numerical analysis. The more points you take, the more accurate your approximation is going to get. The Euler method really can't do any better than this power of h, and that's because we've thrown away all the other terms. In the example that we talked about a little bit earlier, what I've done here is I've plotted the exact solution there in blue versus the original approximation we had where n was 5, and then I doubled the number of points. And because Euler's method is a first order method, it's an order h method, if I double the number of points, I should see the error go down by about half. And that's exactly the kind of thing that we observe. There's an error of 16-ish% in the original versus about 9% in the updated one. So all of that is exactly as we expect. Now, generally, if you want to reduce error, again, take more points. That's a basic fact of sampling. Euler's method is great to teach people the very introduction to numerical analysis and numerical approximation of DEs, but it's far too inaccurate to be used in practice. Now, I'll qualify that with there are some very clever, sophisticated ways of using Euler's method to get really high accuracy. But for a very straightforward application like we're doing here, that local truncation error of order h is just too inaccurate. If we want to learn improved ways, then we start diving into the field of numerical analysis and we think about how we can get better and better approximations to these kinds of problems.